Next up, I move on to routing all the decoupling capacitors around the MCU, and this is one of the most important parts of the entire layout process. Even with a perfect schematic, poor decoupling placement or routing can completely ruin signal integrity and power stability. In this design, I'm using a dedicated power plane on the third layer, which makes decoupling both easier and more effective. The idea is that the power plane provides a low impedance supply across the entire board, while the decoupling capacitors locally supply fast transient currents right at the MCU pins. When routing decoupling capacitors, my main goal is to minimize the current loop area. That means the path from the VDD pin of the MCU through the capacitor and back to ground must be as short and as direct as possible. The smaller the loop, the lower the inductance, and the better the capacitor can do its job during fast switching events inside the MCU. For each VDD pin, I place a 100 nanofarad ceramic capacitor as close as physically possible to the pin. Ideally, the capacitor is oriented so that one pad connects almost directly to the VDD pin, while the other pad drops straight into the ground plane using a short, dedicated via. This avoids long shared ground paths, which can introduce noise and ground bounce. On the power side, the VDD pad of the capacitor connects to the power plane using its own via. Since the power plane is on the third layer, this gives me a very short vertical connection from the capacitor to a low impedance supply, which is exactly what we want. This vertical current flow, down into the plane and back up through ground, keeps the high-frequency currents tightly contained. I also make sure not to daisy-chain decoupling capacitors. Each capacitor should serve its own VDD pin directly, rather than feeding through another capacitor or a long trace. This ensures that each section of the MCU has its own local energy reservoir. For the analog supply pins, such as VDDA, I follow the datasheet recommendations carefully. Even though this design doesn't require heavy filtering, I still make sure the decoupling is clean and isolated from noisy digital return paths as much as possible. Using a solid ground plane directly under the MCU and a dedicated power plane just below that gives the MCU a very stable reference environment. This greatly reduces voltage droop, EMI, and unpredictable behavior, especially important when running high-speed peripherals like CAN or timers with tight timing requirements. Once all the decoupling is routed correctly, the MCU power distribution is essentially locked in, and the rest of the routing becomes much more predictable and stable.